to the cloud.
All right, welcome everyone. This is hopefully, actually no, hopefully it's not our last workshop for the EE team. I do plan on doing one more. I don't know what it's going
Woo!
to be yet. It's probably going to be a judgment call from the EE team, see what they want, and then I'll do a video on that. Anyway, so today we're going to go over a couple of things, and I'm going to share my screen right now to show you what that is. All right, cool. Wait, which one do you see? Do you see the table of content?
Yep, we see the slides.
All right, sounds good. Yeah, so today we're going over 6 topics. I'm going to teach you some circuit analysis stuff. We're going to do some circuit analysis stuff together so you guys can get we're ready to do some analysis when you guys, draw your own circuits and stuff. And then after that, we're going to go into voltage regulators, buck converters, boost converters, fuse and relays, and batteries. These are one of the essential components that you do need to know as to build like a power distribution team for a very simple system. Anything beyond these types of electronics is kind of way beyond our scope of this project essentially. So knowing these components is going to help you figure out what you need to do. If not, yeah, it should be enough to figure out what the power distribution team needs to do. Anyway, so circuit analysis. Here's a kind of a breakdown of what you for those who have taken circuit analysis already for either ME or EE. This is kind of like, I guess, the overall summary of what you should have learned in your ME, your circuit analysis class, at least for your introduction one. You should know your Ohm's law, which is essentially is V equals IR, and you should know your power rating, because VI, and there's a lot of different methods that you can use to solve circuits. There's Kirchhoff's current law, there's Kirchhoff's voltage law, and node analysis. There is one more. It's called mesh analysis. I'm not a big fan of that because most of the time when I was taking the class, I only end up using these 3 analysis, and it took me very far. I'm like, you don't really need to know the rest too much, the other types too much. And you need to know the differences between parallel and series resistors. Parallel, let me write this down. Parallel circuits. Voltage, current, okay, characteristic. So when it comes to parallel circuits, what you have is constant voltage, or meaning, in other words, what I meant by that is that your voltage going through here, the voltage going through here, they're same. Okay, same. However, your current going through here to each resistor are different. Okay, they're not. Current at 1 and current at 2 are not equal to each other. Okay, however, your voltage at 1 and your voltage at 2 are equal to each other, and this go the same way for your series, but in the opposite way. So instead, what you're gonna have for series circuits is that your voltage is not constant, meaning they get dropped. Okay, meaning let's draw this. After it gets past the 1 resistor, it gets dropped. Your voltage drops over here. It drops further. So so your voltage is not constant throughout the entire circuit. However, your current for the entire circuit is constant. Okay, so it's kind of the polar opposite of what series and parallel circuits like. They're opposite to each other. They're also different. Also, when it comes to calculating the equivalent resistance, So there's actually a, well, let me write this down first. Current constant, okay, or same. The way you calculate resistance for a series is essentially just by adding 1, 2, and that's the C. What was that? You simply, simply add them together. When it comes to parallel circuits, it's different, as you can see in the picture right here. Okay. If I move on. Okay. Yes, it's different. Most of the time, there is an equation that you should memorize when it comes to parallel circuits when you're adding them up, which is this. Which is if you have 2 resistors in parallel, you can just use this formula to figure out your total resistance. Okay, it's probably the easiest way to do this. So let's just say you have a circuit where you have 3 resistors, right? You're like, does that mean I cannot use this rule? No, you still can. Just take care of 2 at a time. You know, take care of these 2 at a time. And then after that, it becomes what? It becomes just it just becomes 2, right? And then you take care of this after, and then it will just be 1 again. So this works for any circuits in parallel, no matter how many elements you have in your circuits in parallel. Okay, and series is very straightforward. Okay, so with that said, we're gonna do some examples where we're using these laws to analyze. And I'm gonna give you one example of my own, and then we're gonna do an activity together to have you guys engaged. So let's do that real quick. I'll go over what this is later on, because this is basically how it's gonna, like, everything that I'm gonna teach you right now in terms of circuit analysis is gonna help you understand this very well, hopefully. All right. So before I could move on, is there any questions? You good? Okay. How many of you guys taking circuit analysis class already? Just so I know how much detail I should go over.
Nope.
Oh, okay, awesome. That's even okay. I'll go more into details. So here's the first problem, or first circuit that I want you guys to take a look at. So this is going to be your 60 volts. And you're going to have a resistor here. Okay. And you're going to have another resistor here. Okay, so in reality, like in actual world applications, like, obviously we're not always using resistors, right? We're using like electrical components, right? So think of these as like electrical components, like a camera or TX2 or things like that, okay? That's basically what they are. Yeah, it's often get misunderstood. And it's also important to notice that in these problems, all of these resistors has a constant. They're not like the resistance, like are not changing. Like meaning like your resistance here is like 30 ohms to 40 ohms. They don't vary. Like in real applications, most of the time they do vary. For example, your motors, they draw current, right? They give you, they tell you that it consumes 12 volts, but your current rating changes depending on the situation. Sometimes it's like 18 amps or 5 amps. Really depends on your situation, right? And you can calculate your resistance. Remember, your voltage is V equals IR, right? So your resistance here is basically your 12 volts over 18 amps. And that is your resistance, okay? That's your resistance right here, assuming if this is like where the motor is, okay? So this is what's going on. So when it comes to applying like real applications, it's important to figure out how many amps you're drawing so you can see like the resistance value and stuff. But yeah, that's just a little I guess little tip of how you should see things from textbook to robotics projects, I guess. Anyway, so what you see here is it's a circuit, right? And the first step is to actually identify nodes. Nodes. Now you may be asking, what's a node? Well, let me pinpoint what they are here. There's a node right here. There's a node right here. And there's a node right here. Okay, so you might be asking, okay, what did they help? Like, what did they all have in similarity, right? So you should know that at all of the points I drew, that's where all of the electronics are connected to. It's like an intersection, right? So they all intersect right here. They all intersect right here, and they all intersect right here, like this entire thing, right? So that's their intersections, okay, of two or more electrical components, right? At this point, you have two electric components, battery and resistance 1. Here you have 3, and you have over here you have another 3. Okay, so those are really important to identify, because if you don't identify them, you're not going to be able to understand the relationship, like of how all of these are connected. Okay, so that's the first step, is identifying your nodes. Okay, and there's 3 of them. 1, 2, 3 nodes. Now we're going to next assign direction of current and loops. So right now what we're going to do is apply Kirchhoff's current law, which is this one, KCL. If you guys remember on the slide, it's this one right here, KCL, Kirchhoff's current law, KCL. Okay, so we're gonna apply that right now. For some of us, as a review, if you had taken the class already. So if you guys do know what I'm doing, you guys can, if you see a mistake, let me know. But I kind of worked this out prior, so they shouldn't be any mistake. Anyway, so like I said, the first thing to do is identify direction of which you want to analyze this circuit. So I like to do things clockwise. So remember that. So I like to do plus minus, but you gotta keep it consistent. Okay, plus minus, and then you're gonna draw your loops of the direction of which you're taking. So I'm gonna take this way, and take this way. One important thing when you do this analysis is that loop 1, loop 2, is that if you're gonna make this one clockwise, make other like boxes that you see also clockwise. Do not change direction in loop 2. It doesn't work. Okay, this is a method. There's no logic behind it. It's just a type of method that kind of helps you solve the problem efficiently, if you will. Okay, so you're gonna see this right now. Okay, you can see how Kirchhoff's current law works. So let's get into it. So here are the givens. Your givens are resistance 1 is 4 ohms, resistance 2 is 6 ohms, resistance 3 is 8 ohms. All right. So you're trying to find, what we're trying to find right now is voltages and currents of all of like voltages, voltage 1, voltage 2, voltage 3. And we're also going to find current 1, current 2, and current 3. All right. So that means we have what? 6 unknowns. So that means we need to basically pump out 6 equations to solve all of these variables. Okay, so that's a key here. We need 6 equations. That's a lot, right? And it is. So let's see if we can do it. Yeah, so let's see. All right. Oh dear. Anyway, so you guys can still see it. I'm just gonna use this part right here. Okay, and part 3 is gonna be 8 ohms. Okay, so we're gonna look at the node here. This is called. So I said we're gonna do current Kirchhoff law, but we're gonna do it's kind of combination, but this is called nodal analysis. It's where you analyze each node. Okay, you can analyze node 3, node 2, node 1, but right now what we're gonna do is focus on node 2. And why node 2? Because it's connected with all of the 3 components together, all the resistors together. So we're going to be able to figure out all the information we need, more likely from them. Okay. So we also need to identify the direction of current that's happening. So first of all, there's current going this way, that's I1. There's current going this way, I2. There's current going this way, I3. Now, the question you may have is that why is there 3? You know, like if we could have just considered like this entirety right here, like this first box as like current 1, right? That's like because they share the same, you know, they're all connected in wires and stuff. But you got to remember that what you see right here in the picture is that you have 2 resistors in parallel. So we should know that the current is going to get split up, right? They're not going to share the same current. So that means that 2 and 3 should not be the same. That should have given you a hint, right? At the same time, your current 1 should not be the same as well, because that's coming directly from the battery source. So that's me, because basically 2 and 3 is going to be, when they add together, when current 2 and 3 are added together, it should be equivalent to current 1. Now, what I may have just said may have confused you further. So this is what the nodal analysis is going to help you figure out, right? So what we're going to do is look at node 2. Node 2 is right here. And the thing that you got to think about is like, okay, what's coming into that node and what's coming out of that node, okay? What you should notice is that the current 1 is going in. So that's going to be a positive value, okay? Current 1 is going in. Current 2 is coming out of the node, right? So it's going to be a negative. And current 3 is also coming out of the node, so it's negative I3. And that's basically equal to 0. So remember how I told you that current 2 and current 3, when they're added together, they should be equivalent to current 1 because resistors 2 and 3 are in parallel. Well, you see this relationship here, right? All right, so this is the beauty of a nodal analysis. It kind of helps you figure out, not think about the theory too much, just kind of like helps you figure out the equations, right? But they all come back together. Okay, so this is one equation. So I'm going to box it. And we're going to focus on the next equation. Any questions so far up to this step?
Hey, so Gary, so for the current, the reason that it's like in that direction is because of the battery, right?
Actually, it doesn't matter the direction of which you draw your current. It just needs to be consistent. So let's just say you decide to do it the other direction. All of the arrows need to be facing the other direction. It's really arbitrary.
Oh, okay. Gotcha. Thanks, Gary.
Yeah. I just picked this direction because I like to have things clockwise, but you can have it go counterclockwise too, where all of your arrows could be pointing out like this way, this way, this way. You know, you can do that too. It still works. But yeah. Anyway, so hopefully that kind of did not confuse you any further. Um, anyway, so the next thing to do is now look at each loops. We're gonna look at loop 1 and loop 2. Okay, this is this is where we're gonna figure out what's going on. So over here, we're gonna look at in this loop we have 3 components, right? The battery, the 2 resistors. So we're gonna check out basically each element in this loop. So let's just start with the battery. It doesn't matter where you start, but I'm just gonna start with the battery, okay? So going on the battery, what you'll notice is that since I'm going clockwise, the negative sign right there is first, right? So I'm gonna indicate that as negative 60 volts. Okay. Hopefully that's pretty good. Okay. And then we come here to resistor 3. And then remember, I gave them signs already, right? Plus, I said plus, minus, plus, minus. So if you go clockwise, it's positive here first. So it should be plus, oopsie. Let me positive plus voltage 3. Okay. And then so on and so forth, right? Over here is me positive voltage 2 equal to 0. That's your second equation. All right. And same thing again. I want you guys to help me with this one. See if you can figure out how I'm writing this in loop 2. In loop 2. So what should be my first one? I mean, if we're gonna observe resistor 3, what should is it positive or negative?
Is it going to be negative? Oh, oops.
Wait, so are you confident with that answer, or are you like?
Never mind. Maybe it's positive.
Okay, yeah. So it's going clockwise, right? So it meets the plus first. You know, if that makes sense? Does that make sense, Abel? Because
Yes.
clockwise, right?
Mm-hmm.
So that means I'm looking at the positive sign first, and then negative signs comes later. So basically, that's positive R3, but since we care about voltage right now, it's going to be voltage 3, right? And then the next thing is going to be what? We're analyzing R2. What's the sign of R2? Or voltage 2?
Is that one going to be, oh, negative?
Yeah, negative equal to 0, right? So that's your second equation. The third equation, I mean. Now you're gonna be asking, where are you gonna find, the other 3? Well, there's Ohm's law. Okay. Ohm's law is pretty good equation. So basically, this can give you 3 equations because we have 3 resistors. So that means that V3 is equal to I, or I shouldn't say I because I put it as lowercase I. So we I3 and R3, and V2 is going to be I2, R2, V1 is going to be I1, R1. Okay, so those are your 3 equations right there. Okay, so now you have a total of 6 equations, and you are ready to solve you're ready to solve each voltages and current that's going through this entire circuit. Okay, so that's how you basically analyze basic circuit like this. So yeah, so now we're gonna go into a different topic, but of analyzing circuits too. It's really important. So I want to get into it a little bit. So does anyone have a question with this nodal analysis and Kirchhoff? Oh, this was actually not Kirchhoff's current law. It was voltage law. Now let me explain why that is. It's because when we were doing loops, we were looking into voltages, not current of each element. Anyway, are you guys good on this, or do you guys want me to explain further on what I just did?
It's all good. Thanks, Gabe.
Okay. Thanks, Abel. I appreciate your participation. It helps.
It was good, Gary.
All right. Okay. Awesome. So the next one is called voltage dividers and current dividers. Okay. The reason I want to go over this is because it's going to make your circuit analysis life way easier than it needs to be. Meaning you might not even, you may never have to use Kirchhoff's current law, voltage law, or nodal analysis, all that. Like, if this is too confusing for you, then you should at least remember voltage and current dividers, because they're going to save your life, at least make your life easier when it comes to analyzing circuits. Okay, so here we go. There are little shortcuts, little caveat to your circuit analysis class. If you guys didn't take it already, or I don't know. I'm putting a lot of resistors on purpose, so. Okay. All right, so resistors 1, resistor 2, resistor 3, resistor 4, resistor 5, resistor 6. Okay, so you have 6 components. This can look very daunting at first, right? But remember, you have to start recognizing which one of them are in parallel, which one of them are in series, okay? Because that is going to help you figure out what the hell is going on. So the first thing is to do that. Recognize which one of them are in series and which one of them are in parallel. So the first thing you want to stay away from the battery first, okay? That will be like the last area of which you want to get to. So you're gonna go furthest away from the battery, which in this case is gonna be your resistor 5 and 6. And what you should notice by now is that resistor 5 and 6 are in series, right? Because they're all connected in one line like this, right? They're in series, so you can simply add them together, right? Because that's the equation of adding resistors together. And then you should notice that it's in parallel with resistor 4. So this is the indication of how you represent parallel circuits. You put two vertical lines, and you put R4, okay? And then what you'll notice that after you have this, your R4 is in series with R2. So that means you add R2, okay? And after that, what you should notice is your R2 is in parallel with R3. So you do it parallel. And then after that, you should notice that your R3 is in series with R1. So any questions on how I just did this? I know I just kind of ran through it.
Wait, are you dividing them all, or?
Yeah, so basically what I'm trying to do right now is I'm trying to turn this entire circuit of a really complicated circuit into something that looks like this. Basically, this is what I'm doing. Okay, so I'm basically adding all of these resistors up into one little section. So that's easier to understand how much voltage is going across this component, all of these components, you know? Does that make sense?
Yes.
Okay. So, yeah, so we're gonna go from left to right. But first of all, we need to have some givens. Right? Givens are resistor 1 is 2, resistor 3, 2 is going to be 3, resistor 3 is going to be 5, resistor 4 is going to be 6. Okay, I need to go faster. Okay, resistor 5 is 2, resistor 6 is 1. These are all ohms. Okay, so let's plug in 5 and 6. That's what, 3, right? 3 ohms in parallel with R4. R4 is 6. Remember, when you multiply two resistors in parallel, it's the equation this, R1 plus, sorry, not plus, R2 all over R1 plus R2. This is resistor total for parallel. This is the equation, okay? So basically what you're gonna do here is 6 times 3 all over 6 plus 3, okay? So what does that give you? 2, right? 6 times 3 is 18, divided by 9 should give you 2. So what you have now is 2, right? 2 plus R2 in parallel with R3 plus R1. Follow me so far? Well, I hope so, because I don't see any comments or anything. Okay, I'm just gonna keep going. Anyway, so 2 and R2 is in series, right? Because they're adding together, so we're just gonna do that. So 2 plus R2 is 2 plus 3. That should give you 5, and that is in parallel with R3. Okay, what's R3? R3 is going to be 5, so it's 5 times 5, all divided by 5 plus 5. What does that give you? 25 out of 10. That's a decimal answer, and I believe it's going to be 2.5. Yeah. Right. Okay, so right now, what you have now is a circuit that looks like this. Now that we've broken it down so much, it's going to look like this now. Remember that we just solved for, so this is what we have right now. We have 2.5 plus R1. Okay, this is what we end up, this is what we got to. We got from here to here. We got from there to here. So what does that look like visually? And I'm going to draw it for you right now. So what just happened is this. You have a battery, plus minus, resistor here, okay? And then you have resistor 1 and 2.5 ohms here, okay? That is exactly what had happened. So now it's so easy for you to actually, for you to draw, for you to figure out voltages and currents, right? Because you should know, first of all, you should know that current here is constant, right? Because it's in series. So current is constant. However, there's a voltage drop. V1, V2. Okay? And here is where the voltage divider equation comes in very handy. voltage equation allows you to find voltage drop of resistor 1 or voltage 2 very easily. And this is the equation. So if you want to find voltage 1, it's just going to be resistors 1, resistor prime, I'm going to call this resistor prime, plus, and I should call this voltage prime instead of voltage 2. And voltage 1 times V source. This is your V source, okay? Your 6V, your V source. So that means that you can figure out voltage 1 drop very easily now because it's just a simple equation. You can also find voltage prime very easily too, just by doing this. It's going to be R prime over R prime plus R prime, R1 times Vs, okay? Basically, this equation right here is called voltage divider. Because you're dividing voltages across each, so you're basically kind of subtracting voltage drop at each resistance. You can apply this logic anywhere on the circuit. Okay, you can apply here, 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 and helps you figure out essentially help you figure out the voltage across each resistance very, very fast and very easy. Actually, it's not very fast. It's tedious, but but it's easier to kind of comprehend than the Kirchhoff's law, the KCL, and nodal analysis and stuff. But it's tedious, but it's easier to process in my head. Hopefully, it's easier. Now, what's a current divider? I'm not gonna I'm just gonna give you how it's applied instead of giving an example because we don't have time. So when it comes to the current law, the current divider, I mean, you have this. Okay, you have resistance. Okay, and there's a current goes through here. Current goes through here. Current 1, current 2, R1, R2. Okay, and this is your current source, I source. You're like, what the hell is an I source? Like, we never seen that before, or have we ever used it before, right? So think of I source as this. Oh my God. Think of I source as this. Imagine, not imagine, just consider this is what I'm saying. You should know that there's there's current 1, current 2, current 3, and you want to figure out the current of I2 and I1 and I2, and your I3 will consider your current source, and you could, because your current 1 and 2 are in parallel, right? So this this particular part right here, is actually the same as this setup right here that I just drew. It's the same thing, okay? Like current coming in gets split up into two. Very similar, no difference, okay? So this is what I mean. You can use current divider and voltage divider law really well. If you know how to use it well, then you kind of have the ability to solve any type of circuit very fast. Anyway, so for the to figure out the current of at I1 is going to be like R2, R1 plus R2, and current source. So the difference between the voltage divider and the current divider is that if you want to find the current of R1, make sure your numerator is R2, okay? Whereas in voltage, if you want to find the voltage drop at R1, your numerator has to be R1. If you want to find the voltage drop of R prime, it needs to be at R prime here. Over here is the kind of opposite. If you want to find the current of R1, you need to have the R2 as your numerator and vice versa, okay? So that's essentially how you will be, these are the type of methods and tools you can use to analyze circuits. Okay? And now I'm going to go back to here. How does this all here relate to this? This is a picture of how the TX2 board is made, okay? So the DC jack is basically your voltage, the outlet that you have in your, that get plugged into your wall, and then they have it has a transformer and a rectifier that converts the AC current from your wall outlet into DC current, okay? You know that bulky little black thing that you see in those bigger appliances, like your AC unit or something, or your AC unit. You have those little bulky little, or your laptop actually has this little block bar. Those are basically converting, not just it also does other stuff too, but it converts AC power into DC voltages. Okay. Anyway, so what you see here is that you have a split, right? That should also indicate that the TX2 right here and these two power sources are in parallel. Okay, so you'll be like, wait, I thought that the entire thing is the Jetson TX2. Oh, sort of. This Jetson is like your CPU, okay, or your processor, okay, and this is like your power source that's going to be plugged in to other electrical components like your USB 2.0, USB 3.0. So if I were to draw this out, it's gonna look very messy, but I'm gonna draw at least the first few steps of how the board is gonna look like, so you guys have a better understanding. So this is your DC, okay, and what you're gonna have is coming out is going into your Jetson first, and then you should know that since we know that this is gonna be this is in parallel with this guy, right? So we're gonna put that in parallel. Cool. So this is TX2, and this is gonna be your TPS whatever, right? And then what you should also know that after you follow through, you have these purple lines all being divided. You see? That's a lot, right? Those are all in parallel. So that means you're gonna have a huge stress. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 resistors, all in parallel. Okay, and they all get divided back to your DC thing. This is how the TX2 is set up, and it's kind of shown in the neatly matter because obviously they don't want to show it like this, right? Not like the way that I drew. That's too messy to understand. So they drew it like this for us to better see everything of how everything's connected. But essentially, what I'm saying is that you can actually do a circuit analysis just by looking at this chart here. But it's very daunting, right, to begin with. But yeah, so hopefully that helps you kind of relate how your circuit analysis class come in handy when it comes to these projects. Okay. All right. Now I'm going to go over other parts of the slides. We just went over the introduction of circuit analysis. Now I want to go over voltage regulators and other stuff. Any questions before I go further? Did you guys fall asleep?
Hola?
Okay.
You.
Sorry?
Yeah, were you talking to me?
No, I mean kind of everyone because no one's replying. So I'm just like
You're doing good.
Okay.
Yeah, we're good, Gary. Sorry, yeah, I had to do something real quick, but yeah, I understood the voltage divider. Seriously, this is definitely going to help me out in physics too. At least the first part.
All right. Oh yeah, if you need help with circuit analysis class, you can come to me too. Anyway, voltage regulators, what are they used for, and what do they do for us? You know, like why are they so important for us to consider when it comes to power distribution? Well, I can certainly say that we shouldn't be using for our project, but it's important to look into it because it's important to look into it because there are many variations of it. We're only covering the most commonly used voltage regulators. And when we look into other branches, it will help you figure out what we need. Anyway, so the one that's most commonly used is called 78XX. Okay, I don't know why it's called 78. They just named it that way, but the XX is where it's important. Okay, XX represents the type of voltage that you want to have it as your output. Okay, so I don't know if you guys can see, but in this picture it says 7812. Okay, 12 is your voltage output. Okay, this is your voltage output, meaning that whatever voltage that is coming from the battery, usually the voltage that you get from your battery is not constant, right? Because like over time, it's going to have a voltage drop and so on and so forth because it's losing, energy. It's losing energy, so it's not constant. It's going to fluctuate. So what this voltage regulator does is making sure that before it gets to any type of electronics, it stabilizes that voltage rating. So when it says 12, if it gets through, say, battery here, if it gets through here to electronic here, it makes sure this electronics get a consistent 12 volt at all times. Okay, that's the beauty of it. The downside of this is that they have a very whatever current that's coming in from the battery is going to be having the same amount of current that's coming out, right? So that's a downside because let's just say your battery is say 24 volts, right? And then this is 12 volts. And if your current is staying consistent, that means you're losing a lot of power, right? Because power is what? Voltage times current. Over here, voltage times current. Your P2 and your P1, there's a huge difference. That huge difference translates into heat. Okay, hence why they look like this. Hence why they look like this. Real applications. What you see right here is a heat sink. Okay, that's heat sink that's connected to the voltage regulator. This allows heat to be dissipated in a very efficient manner. And if you're taking what classes like heat transfer, these are fins. Okay, it allows heat transfer to be more efficient, right? So anyway, that's a little bit of heat transfer class coming into EE related stuff. But yeah, so that's the downside of using voltage regulator if you're dropping into a really low voltage. So you don't want that. Okay, but it's really good for small appliances like stereo, right? Because stereo has very low amperage, which is really good, and they don't really require that much voltage to begin with. So you can just use like your 5-volt battery to go 3.3 no 1.8 voltage AA battery, I think, to power some of the electronics. Anyway, but capacitors are used to kind of handle the noise of I guess your voltage much better. It's this is more important to consider if you're working with sensitive applications like audio. But for our case, I don't think it's going to be an issue. But anyway, that's what voltage regulators are essentially about. That's what they're used for, to basically regulate how much, to make sure that the electronics that you're trying to power up has a consistent amount of voltage. Okay, now boost converters. They're very important, I would say. Okay, how should I go about this in a really good way? Okay, so this particular part right here is called MOSFET. Just think of MOSFET, at least in this situation, as just a switch. Nothing else, just an on and off switch. Okay, this is your capacitor here. And you should know capacitor stores energy. Okay, and this is a load or anything that you're trying to power electronic. And your inductor here. This is your inductor. Inductor also stores energy. So what you notice is that inductor and capacitance, they both store energy, but they both store it differently. Inductor uses current to store energy in its magnetic field, whereas capacitor uses voltage to store to get a gradient in voltage and store it, okay? Store it in its internal resistance, I think. I'm not too sure. Anyway, so the way it works is that so this is your battery here. And is supplying current. So when this switch is on, meaning you have a complete circuit here, what does that mean? Well, that means that your inductor here is going to be having a huge load of current going through, right? Because inductor is not a resistance, right? Because it's not going to like cause the current to stop, like to stall. So because of this fast current that's being provided into the inductor, it's going to be storing as an energy, okay? But once the switch is off, like here in this picture, in the second figure, what's going to happen is that now all of that stored energy wants to be released, right? But it cannot be released immediately. It has an acceleration. And so with acceleration, there's going to be a force and how much current is being applied in the circuit. So basically, this stored energy is being now distributed down to your capacitor and your load. So what ends up happening is that because of the stored energy, what you end up getting is voltage that is higher than the voltage that's been provided by the battery. So basically what the boost converter did is kind of increase your voltage rating so that when you have appliances, let's just say 24 volts and you have your battery is only 18 volts, you can use a boost converter to get to 24 volts for that appliances using a boost converter, okay? Most of the time, people don't use boost converter. They just pick a higher battery and then just drop it down by using buck converters. Anyway, this is once it is off, it gets provided. Now it completes this circuit, but afterwards it's going to turn back on again. Okay, and so because it wants to turn back on, because it wants to continuously store that energy, because that stored energy is what's causing this an increase in voltage on the load. But what is this capacitor doing here? Well, capacitor is making sure that once the switch is on, the capacitor can then distribute or discharge its stored energy into the load, buying some time for the inductor to store energy again. That's all it is doing. So basically, and between these two circuits, it all depends on the timing of your switch here. So the longer you have it on, the more stored energy you're going to have. In other words, the higher voltage of which you're going to have your load to have, want to have, essentially. Okay, So that's how the boost converter works. Buck converters is exactly the same thing. It just the only difference is that your 4 components of which are all in different places. So the 4 key components of a buck converters were inductors, capacitors, transistor, and a diode, which are all the same, which are all the same components that the boost converter have, but now they're just in a different order. So the transistors here are instead right here, and then your capacitor is still the same place, but your inductor are instead right here. Okay, so the because of this rearrangement, what we end up having is a component that is able to drop voltages to a desired level that we want. So that's something that that's actually something that we must have to that we do have to do in our application. So this is something we have to look into for the power distribution team, no matter what. And fuses and relays. Okay, I gotta go faster, I guess. Fuses and relays are essentially, they're not the same. I want to point that out first because sometimes people get it very confused. So they're not the same. In fact, they're very different. Fuses are basically like a little circuit that makes sure that it causes a circuit to become from closed circuit to open circuit. Okay, because if you're, sometimes it's unpredictable of how your electronics are going to behave, right? Because you can't see it, right? So a fuse is used to make sure that if the electronics draws too much current, it's going to basically have the circuit become closed to open, so that no more electricity will go through an electronic that is consuming too much current. Because if you allow that to happen, your wires are going to heat up and catch on fire. So this is why we have fuses to begin with. Now, for relays, the reason we have relays to begin with is they're a great solution to our problem of which we need to develop, which is to solve it as a mechanical switch. We can use a relay, or we can use a relay for mechanical and wireless switch as well. So this is a solution we may go after, but the thing is that the purpose of using a relay is to account for voltage drops, not because we want to treat it as a remote controller, right? Because we can easily use a simple switch to turn on and turn off something. So why do we use relays? Well, relays are actually accounting for the voltage drop that occurs through a long wire. In fact, relays are not commonly used in robotics. They're mostly used in automotive because we have electronics that goes everywhere, and like in a lot of places in the car. So you need to use long wires, but long wires means that you're gonna have voltage drop because there's internal resistance in your wire, and you don't want that because once, let's just say you have a battery here, you have an electronic here, and this is like 30 feet, like just supplying 12 volt here. What's going to end up here is that probably like 11 or 10.9 volts, but this battery, this light bulb, say, needs 12 volts. So if you're only providing this much, what's going to happen is that the life of your bulb is going to decrease. Let's just say you have an LED, which is supposed to last a very long time. But if you don't supply a sufficient amount of voltage, battery life of this light bulb can dramatically decrease. This is how you can tell if you buy an LED in your house and it says it can last like 5 years and it only lasts for 2 or 3 years, it probably means that your light bulb is not getting sufficient amount of voltage that's required to have it last that long. So yeah, that's you should call your power distribution line to complain about that if that's happening. Anyway, so that's what the relays are mainly for, is to prevent this by basically reducing, by having a little switch here and then have a relay here that makes sure that your 2 feet, your distance from actually your circuit is now is much shorter now because of the relay, so that you don't have to worry about this voltage drop anymore. That's what the ideal relays are. Not to really treat it as a mechanical switch, but more as to account for the long distance in wire. And lastly, we're going to go over batteries, and I have 5 minutes or less. So there's obviously a bunch of different batteries out there, and the ones that we care about is lead acid. And the reason that is because, first of all, we can't use alkaline. We cannot use alkaline because it's way too small, and we have bigger appliances. So this is not even in our head. And plus, we want to be rechargeable, right? Because we don't. This is not a one-time thing. But why did we not use these? You know, why is it this? Why did we not use these at all? Well, it's because they allow us to. What they're known for is allowing appliances like brushless motors, which requires a lot of amps. So what these batteries allow you to do is discharge a lot of amps in a very short time. So because of that, they're also known to be very, very easily to explode because of how much amps they can discharge. So it's also dangerous to use them. And but for our case, lead acid is enough. You know, it discharges in a sufficient amount of time, and it has a lot of capacity. So and it's rechargeable. So that's why we went with lead acid. And it's although the only downside is that it's very heavy. And then I'm gonna go over how basically you read these specs, and how you're supposed to interpret them. So in a lot of batteries, they have these reading here, 12 volts, which is saying that it's supplying 12 volts. So there's nothing fancy there. But what's confusing here is this: 55 amp hours over 10 hours. Like, what does that even mean, right? So what that means is that it can do 55 amps in 1 hour. Okay. But what does this 10-hour mean? That means that you basically need to divide it. So if you want this battery to last for 10 hours, whatever that thing that you're applying to is to be only drawing 5.5 amps, and then only then it can only last for 10 hours. Okay, but this is all theoretical values. They have data sheets like this right here to help you determine how the battery is actually performing, because one battery from another, they're very different. They don't all perform the same way. So it's always good to refer to a chart that they provide you with in the data sheet, because those are more accurate. So hopefully by now you understand how to read this. I do have an example of batteries that I want you to look at really quick. So right here, there's batteries here that I hopefully you guys can understand. So right here, this particular one says 12 volts, same thing, nothing special, 18 amp hour and 20 hours, right? So like I said before, this shows that this can draw 8 amps per hour. Okay, I did not tell you this before, but there is a variation to this. Let's just say your application requires 36 amps, right? You're like, oh, this only allows 18 amps per hour, so it's not gonna it's not enough. I need a higher amp rating. No, you don't. What's happening here is that 36 is twice as larger as 18 amps, right? So what's gonna happen is the battery will allow you to draw 36 amps, but in 30 minutes, your time decrease. Okay, so it doesn't. So basically, I'm just saying that the battery doesn't have a limit of how much current you can draw. You can draw as much as you want, but it just depends on the capacity of which your battery has. Okay. Anyway, so but if this was if you want this battery to last for like 20 hours, then you need to what you need to do is it only needs to it can only provide 0.9 amps in 20 hours. Okay. So basically, that's the general idea of how you kind of select your batteries.
Hey, Gary, in the chat, Aaron said that isn't it supposed to be 2 hours and 30 minutes?
No. Why would it be in 2 hours? Because okay, the reason it's not 2 hours because it can only do 18 amps in 1 hour. Okay, hold on. 18 in 1 hour. Remember, you want to have this ratio. You want to have this ratio 18 amp hour. So what this does right here is, let's just say your application requires you to draw 36 amps. You have 0.0 hour here. So if you multiply them together, you still have this ratio of 18 amp hour. That makes sense. So 36 times 0.5 is 18 amp hour. Yeah. That goes with any other stuff too. Like if you want to increase it more, you just gonna have less time to use the battery. Okay. I kind of went 1 minute extra. All right, and I also rushed it a lot too. My bad. Any questions though?
This is mostly like for the power distribution team, right?
Yeah. But even with that, like you're still working with electronics. So I mean, like it's still important to know all of this. So to generalize, I guess to summarize everything that what I just said, what we did today was we went over parallel and series circuits. We learned how to analyze a few of them. By using Kirchhoff's law, nodal analysis, and things like that. We went over voltage regulators. We went over how to use voltage and current divider equations in your circuits. You also learn how boost and buck converters work, when to use fuse and relays, and how to basically select batteries. Hopefully, that was a lot of information. But if you guys have any questions, you guys can contact me on Discord. Simply just message me or through email. It's fine. But yeah.
Woo! Thanks, Gary.
That was kind of it. Hopefully that was fun for you. If not, that's okay.
It was pretty shocking.
Yeah. Anyway, so thank you for your attention. I really appreciate it. And I hope to see you guys next time. Whenever that is. Okay. I'm gonna start the recording now.